We're going to look at telling whether or not a function is continuous at a certain x value given its graph. So this is the graph of a function. It does pass the vertical line test. And so there's a very quick way you can decide these things. So I'm going to call that function f. Is f continuous, so CTS is continuous at x equals 4, say. And what I'm going to do is I'm going to come here at x equals 4 on the graph, and I'm going to have a neighborhood around 4, x equals 4. And then where does that correspond to the graph? Well, that's going to correspond to up here. And then as I travel over this graph from left to right, I never have to lift my pencil off the paper. And since I never had to lift my pencil off the paper, the answer is yes, it is continuous at x equals 4. So that's a really quick way to do that, to answer that, without having to use these three rules of continuity, which we will do later on in the video. I could ask the same question, is f continuous at x equals 1? And again, here's x equals 1 on the x-axis, and I'll get a neighborhood around it, so from 0 to 2. And where does that correspond on the graph? It corresponds to there. And if I start moving from left to right, I'm fine until I get to here. But now to continue on to this part here, I have to take my pencil off the paper. And because I'm not able to draw that without lifting my pencil off the paper, it is not continuous at x equals 1. So at x equals 1 there, I'm fine until I get to x equals 1. Then I have to lift my pen off the paper and then put it back down to keep drawing. So the answer is no. So we should be able to see, is it continuous at x equals 6? And the answer to that one would be no. Because if I start over here moving from left to right, I'm fine. I don't have to take my pencil off the paper. But then when I get here and to continue that drawing, I have to lift the pencil up. And so it is not continuous at x equals 6. And I think you can see for the same reason at x equals -3, it's not continuous. Now let's look at solving that. So that's all well and fine. It gives you a good idea. What if your professor says to prove that it's continuous using the three rules of continuity? Then it's not enough to do what I just showed you guys. So are we continuous at x equals 4? So let's look at the first rule. What is f evaluated at 4? Well, this is your x-coordinate, and I find the point on the graph of x whose x-coordinate is 4, and that point is 4, 2. And then if I want to evaluate f at 4, f maps the x-coordinate into the y-coordinate, so f evaluated at 4 is equal to 2. So the first one is fulfilled. F of 4 does exist. Okay. Now let's look at the second one. The second one says that the limit as x approaches 4 has to exist. So what is that equal to? Well, to get the limit, we're going to have to look at the left-hand limit and the right-hand limit. So what happens as x approaches 4 from the left? So I'm going to find some x values in a neighborhood, so close around, so say starting from here, and up on the y values here, as I approach 4 from the left, what are the y values approaching? Well, the y values are all equal to 2, and they're actually approaching 2. So my left limit is 2. Now what about my right limit? So what is the limit as x approaches 4 from the right? So if I'm on the graph, so here's x equals 4. If I'm on the graph and let's start here, and I'm approaching x equals 4 from the right, what are those y coordinates approaching? And those y coordinates are approaching 2. Now, my left-hand limit and my right-hand limit are the same. Therefore, the limit exists and it is equal to 2. So this second part is satisfied. And then finally, the third part, we have that the limit as x approaches 4 of f of x, we saw from the second part that it's 2, and we saw from the first part that those are all equal. So the limit and its evaluation is equal, and so therefore, by the 3 rules of continuity, the answer is yes. All right, so that's a lot of doing to get it proven. Okay, let's see, is f continuous at 1? Let's use the 3 rules. Okay, so what is f evaluated at 1? Well, this is the x-coordinate, and I look for the point whose x-coordinate is 1 on the graph. And f evaluated at the x-coordinate will be whatever the y-coordinate is, and that will be f evaluated at 1. But when I look at this graph, 1 is not in the domain. There is no point with an x-coordinate of 1. So this does not exist because 1 is not in the domain. There doesn't exist a point with x-coordinate 1. So it breaks rule 1, and so automatically I can say the answer is no. It is not continuous. It breaks the first rule. All 3 of those rules have to hold. Okay, so now let's look at is f continuous at x equals 6? Well, let's prove it by the 3 rules. What is f evaluated at 6? I look for the point whose x-coordinate is 6, and if it exists, then f evaluated at 6 is going to be whatever the y-coordinate is. And you can see you have a point on the graph whose x-coordinate is 6. It's 6, comma, -1. And so f evaluated at 6 is equal to -1. Okay, so the first part holds. Now, what is the limit as x approaches 6 of f of x? Well, I need to look at the left-hand limit. So that's my left-hand limit. So when I get a little bit to the left of x equals 6 on the graph, what are the y-coordinates of these points approaching? The y-coordinates of these points are approaching 5, and so my left-hand limit is 5. Now let's look at the right-hand limit. So when I'm somewhere to the right of 6, so somewhere here on the graph, and it's approaching x equals 6, what are the y-coordinates approaching? The y-coordinates are approaching -1. Now, my left-hand limit and my right-hand limit are not the same. Therefore, the limit does not exist. So, rule 2 fails. And so the answer to that is no. Okay. Now, how about is f continuous at x equals -3? And prove your answer by the 3 rules. Okay, so the first rule, what is f evaluated at -3? I look for the point whose x-coordinate is -3. And then f evaluated at -3 will be the y-coordinate of that point. So here is the point on the graph with x-coordinate -3. That point has coordinates -3, 1. And so f will map the x-coordinate into the y-coordinate, and f evaluated at -3 is equal to 1. So the first condition is satisfied. So we're all good for that. All right, now, what about the limit? So I'm going to need to look at the left-hand limit and the right-hand limit. Okay, so for this second one, whoops, what's the limit as x approaches -3 of f of x? Well, what's the left-hand limit? So as it approaches -3 from the left, here's -3, so get, a little bit to the left on the graph. What are the y-coordinates of those points approaching? The y-coordinates of those points are approaching 3. So the left-hand limit is 3. But now, what about the right-hand limit? So if I'm a little bit to the right of -3, so say here, what are the y-coordinates of those points approaching as they approach x equals -3 from the right? And the y-coordinates are approaching -2. Once again, my left-hand limit and my right-hand limit are not the same. And so the limit does not exist. So the answer to this one is no, it's not continuous at x equals -3. So using the test to see if you have to lift the pencil off the page gives you a quick answer. But if your professor wants you to prove it using these 3 rules of continuity, you're going to have to do more. Okay, so that ends the video. Thanks for watching. See you later.